reaction lab for BYU Chem 353. So just going to go over a couple of key concepts before we get into lab. We're really not doing any new techniques today. So it's all going to be lab techniques that you're familiar with, but there are a few important concepts. So first off, we're going to talk about molecular orbitals, and I'm not going to go into a ton of detail on this. You can find a little bit more information on the lab PDF, so if you have any questions or need information to go back to for reference, there's a good section there in the lab procedure PDF that you can look at. But the general idea is that for a Diels-Alder reaction to happen, the HOMO of one of the two reagents has to interact constructively with the LUMO of the other reagent. So I'm just going to go ahead and sketch out a 1,3-diene to act as our diene, and then I'm going to just draw a simple alkene to act as our dienophile. And these could have R groups on them, and it really wouldn't impact the molecular orbitals. So I'm going to go ahead and draw the HOMO of the diene and the LUMO of the dienophile, but it really doesn't matter. You could switch them. You could draw the LUMO of the diene and the HOMO of the dienophile interacting, and it would work the same way. So the HOMO for a diene for a 4-pi system is going to have one nodal plane. So I'm just going to draw the 4 p orbitals there, and the phases are going to look like this. As you can see, there's one nodal plane down the center of the molecule. The phases switch across that sigma bond. Now, the LUMO on the dienophile is essentially going to look like a pi star orbital. So we're again going to have one nodal plane down the center of the molecule. So now, what you can see is that if you bring these together, one on top of the other, you'll notice that the lobes on both ends interact in phase, which means this reaction can happen under thermal conditions. Now, if we had a system where the ends didn't overlap on both ends in phase, then we would need to use photochemical conditions to be able to make that reaction happen. So you're going to need to, on one of the post-lab questions, you're going to need to look at this, and you're going to need to just draw out the orbitals on both of them and figure out how you can get the orbitals to constructively overlap under thermal conditions. And the orbitals that you'll need are drawn in the lab PDF, so you'll need those for reference. Okay, the second concept I'm going to talk about today is related to NMR and topicity. So we're going to see an interesting example of diastereotopic hydrogens today. So first, I'm just going to take a quick look at cyclohexanol. This is the product that we made in the reduction of a ketone lab. If we draw it out in its chair conformation, we'll notice that these two hydrogens here that are opposite the ring from the alcohol, if we were to change one of them to a deuterium, we haven't installed any stereocenters in the molecule. So looking at the deuterium test in the typical fashion wouldn't work. However, in this configuration, we'll notice that we have a trans product. The deuterium and the OH are on opposite faces of the ring, whereas in this case, we have a cis product where the deuterium and the OH are on the same face of the ring. So the trans and cis versions of a compound are still going to be considered diastereomers. So even though this compound technically has no stereocenter, switching the location of the deuterium still creates two different diastereomers, making those hydrogens diastereotopic. The same thing can apply in more complicated systems. I'm going to draw out for you what's called a Norbornane system. This is a 6-membered ring that's bridged by one carbon. And this is one of the sorts of products that we can make in a Diels-Alder reaction, especially if we had an alkene there. So if we happened to have two groups over here, I'm going to call them R, and I'm going to say that they're the same R group, because that makes this compound meso. It gives it a plane of symmetry. So these two hydrogens here on the bridge, same thing applies. If we have a deuterium here, we could kind of refer to this as the cis compound, because the deuterium and the R groups are on the same side of this 5-membered ring here. And if we swapped them, we'd get the trans isomer, which are also diastereomers. So just get used to looking at this. Even if doing a deuterium test doesn't create a new stereocenter, if it creates cis or trans isomers on a ring, then the hydrogens are probably still diastereotopic. All right, so this is the Diels-Alder reaction. Here are the reagents I'm going to be using today. I have xylene, which is going to be our solvent for the reaction. I have maleic anhydride, which is going to act as our dienophile in this reaction. And then here we have 3-sulfoline. 3-sulfoline is the chemical that's going to release SO2 and act as an equivalent of butadiene. And then finally we have toluene, which we're going to reuse for recrystallizing the product after the reaction is complete. All right, so I'm just going to measure out 260 milligrams of this maleic anhydride. And I'm also just going to go ahead and measure out 124 milligrams of the sulfoline. It's actually 100. Okay, and then I'm also just going to go ahead and measure out 200 microliters of xylene. You can see right there at 0.2. Alright, so now I'm going to go ahead and just add that 200 microliters of xylene to the reaction flask. And then I'm going to go ahead and add first the maleic anhydride that we measured out earlier. And also the sulfoline that I measured out earlier. Okay, so now I'm going to go ahead and hook up this condenser. So we're just going to place the condenser and going to hook up this tube to the sink back here. And then this tube is going to go to the drain. And then we're just going to go ahead and start running water through the condenser. And we're going to go ahead and start stirring our reaction. And we're going to heat this pretty vigorously. So as you can see down there, it's starting to spin, and as it heats up, the crystals are going to dissolve. Okay, so I also have a drying tube here with calcium chloride in it. We're just going to go ahead and stick that on the top to prevent any moisture contamination. Now you'll notice if you look down here at the bottom that all of the crystals have dissolved and that it's actually starting to change color slightly. We've got a little bit of a yellow color in there. That indicates the reaction's proceeding. We're going to continue to heat it up until the solvent is gently boiling, and then we're going to let the reaction run for about an hour. Okay, so as you guys can see, we've now reached the point where the solvent is at a gentle boil. I just turned the heat down just a little bit because I don't want it to get any hotter than this. We just want the solvent to stay at a gentle boil. The reason is because having the solvent too hot can actually cause decomposition of our product and will result in contamination of our final product. Additionally, to demonstrate the reaction is happening, we can actually test, because the sulfolene should be releasing sulfur dioxide vapors as it breaks down to release the butadiene, and we can test that that's happening by taking a damp pH paper and inserting it in here. And as you can see, it turns red, indicating that the SO2 vapors are being generated, so the reaction is progressing. So now, alright, so our hour-long reflux is just finished. I'm going to go ahead and let this vial cool off to room temperature, and then I'm going to go ahead and add some toluene to encourage crystallization. Okay, so I'm going to go ahead and measure out 250 microliters of toluene. So you can see there we're at about 0.25. And now that our reaction is cooled down to room temperature, I'll just go ahead and add that toluene to the reaction vessel. And then I'm just going to go ahead and remove that spin vane. And then we're just going to let that vial sit for 20 to 30 minutes and let crystals form. So it's going to take a little bit of time for the crystals to precipitate, but they will form. Alright, so as you can see here, now that I've added the toluene and let this sit, we actually do have some solid crystals in here. So I'm going to go ahead and collect those via vacuum filtration. So I'm just going to first gently scrape the sides of the vial to loosen up the crystals so they'll come out. And then I'm just going to upend this into the filtration apparatus, making sure that I get all of the crystals out of the flask and into the vacuum filtration apparatus. And then if we look up here, you can see that those crystals have collected nicely on the filter. Okay, so now I'm going to go ahead and recrystallize our crude product from the Diels-Alder reaction. So I have here our crystals. I'm going to go ahead and take these and add them to this test tube. So now we've got our crystals in there. And then I'm just going to go ahead and add a little bit of ligroin. I'm just going to go ahead and add a small amount of ligroin at first. We can add more later if we need to. But I'm just going to go ahead and take this, and then I'm going to heat it up until the crystals dissolve, and then I'm going to cool it off to get the crystals to reform. Okay, so we're going to go ahead and take these crystals that are in ligroin, and we're just going to immerse it in this hot water bath and stir it up. And we're doing this to get the crystals to dissolve as best we can. So as you can see, there are still crystals that aren't dissolving, so I'm going to go ahead and add just a little bit more ligroin. Okay, so I'm going to continue. I've added some more ligroin, and I'm going to continue just heating this up and stirring it until things dissolve. so now that everything's pretty much dissolved, I'm going to go ahead and stick this in an ice bath. And as you can see, it's gotten cloudy, meaning that we're forming crystals again after cooling it off. So I'm going to heat it back up, and then I'm going to let it cool at room temperature until it forms crystals. So go ahead and heat this up. Okay, no longer cloudy. And then I'll just go ahead and set this to the side until it forms crystals. Alright, so now that we've let this sit at room temperature for a bit, we actually, as you can see, we've got crystals in here. So just like I did earlier, I'm going to go ahead and take this and I'm going to vacuum filter it, and then I'll collect it and weigh it, and then we can do the melting point and IR. So just go ahead and end it. Very carefully scrape out all of the residual crystals, so you don't want to leave anything behind. And we have our recrystallized product. Alright, so now that the crystals have finished drying on the vacuum filter, I'm just going to go ahead and weigh them. So I'm just going to scrape these out of the funnel and onto this weigh boat. As you can see, we've got about 53 milligrams of the product. Alright, so I'm going to go ahead and prepare these crystals for a melting point. So I'm just gently tapping them into this capillary tube. So you can see I've got some crystals there in the mouth of the capillary tube, and I'm just going to go ahead and tap those down until they're in the bottom. So after a little bit of tapping, this is now ready to go ahead and be inserted into the melting point apparatus. Alright, so for this melting point, for the Diels-Alder reaction, I'm just going to set a start temp of about 98 because the product is supposed to melt at 104, a ramp rate of 2 degrees per minute, and a stop temp of 170 degrees. And then I'll go ahead and start and get the block preheating so that then I can do the melting point. Alright, so the melting point apparatus is telling me that it's preheated and ready to go. So I'm going to go ahead and take my sample and insert it into one of these holes here. And we'll just go ahead and Alright, so now I'm just going to go ahead and prepare for an IR. So I'm just going to put a few of these crystals on our salt plate. I'm going to very carefully add just a bit of neutral. I'll go ahead and take this and just grind these together. So we've got our crystals nice and suspended. And we'll go ahead and take that and run an IR. Alright, so I'll just go ahead and load this in the IR instrument. Alright, so after running the IR, this is the results that we've got. The file for this will be on Learning Suite, so you can go ahead and print this off and label it.